Hello, this is Jennifer Martinez. In this video, we're going to go over homogeneous linear systems. What is a homogeneous linear system? It is a system of linear equations in the form of AX equals 0, where A is an n by n matrix and 0 is a 0 vector in Rm. A homogeneous linear system always has at least one solution. It always has the solution x equals 0, the 0 vector in Rn. And that solution, that x equals 0 solution, is called the trivial solution. So Ax equals 0, the equation Ax equals 0, this homogeneous system of linear equations, is always consistent because it always has the trivial solution. And why is 0 in Rn, the solution in Rm, versus this 0 is in Rm, is because this homogeneous equation only will work, the definition of A times x will only work if x is an n by 1, because A is an n by n, x is an n by 1, so that's the solution. And the result would be an n by 1. So these are two different 0 vectors. So x is equal to 0, which is in Rn. And this 0 vector is in Rm. It all makes sense. The homogeneous equation, Ax equals 0, has a non-trivial solution if and only if the equation has one free variable. And if it has one free variable, then we know it's always consistent because x equals 0 is a solution. So that means that there would be many solutions here, an infinite number of solutions. To see this, let's look at example 1. Determine if the following homogeneous system has a non-trivial solution. Then describe the solution set. So here we have a homogeneous linear system of equations. They're all zeros here. So let's go ahead and solve that. So I put this in my augmented matrix form, and I'm going to not get a 1 here in the first row, first column, since the numbers below it are multiples of 3. So I'm going to get a 0 where that negative 3 position is. So I'm going to just add them together. Get 0, 3, 0, and 0. This row, this last column here, will always be 0, won't it? To get my third row, I'm going to take negative 2 times row 1, add it to row 3. To get 0, negative 10 plus 1 is negative 9. And then we have here 8, negative 2 times negative 4 is 8, plus negative 8 is 0. And then we always have that 0 there. So now I have a new pivot. I might as well I could make that a 1, but since negative 9 is a multiple, I'll just multiply the second row by 3, add it to the third, leaving my first and second row alone. And then I'm going to take 3 times the second row, add it to the third row. So we get 0. 0, get a row of zeros. So x3 is free. We can see x2 is 0, but x1, we have here 3x1 plus 5x2 minus 4x3 equals 0. x3 is free, x2 is 0. So I'd have 3x1 equals 4x3, or x1 equals 4/3 x3. Now I could have row reduced this, but since that was simple to do, since it was 0, I decided to just go ahead and stop here. So there I have it. There's our solution. x1 is 4/3 x3. It's in terms of x3. So therefore, this homogeneous system does have a non-trivial solution, which agrees with the statement here, because it has a non-trivial solution if and only if there is one free variable. x3 was free, and it does make sense because x3 can be anything. x3 can be 0, and you'd have the trivial solution. x3 could be 1, and then x1 would be 4/3. x3 could be 3, and then x1 would be 4. So there's an infinite number of solutions that you can choose here. So now let's describe the solution set. So I'm going to rewrite the solutions to describe the solution set. I'm going to rewrite them in a different way now. There's 3 variables, so we know that x has to be in R3. And x1, well, we know that x3 is free, so I'm going to leave it. x2 is 0. I know I'm going backwards there. But x1 I'm going to put in terms of x3. And then what I'm going to do is factor out an x3. And what I get is a vector 4/3, 0, and 1. You could have also factored out a 1/3. So let's do that just to see that over 3. And then you would get 4, 0, and this would be a 3. Makes sense? Because it would be 3/3, factor in a 1/3, and you multiply that through, you would get that. So either one of these is fine, whether you want fractions or not. This represents this vector times a constant describes the solution set of this homogeneous system. So those are the 2 answers. What does this look like? It would be a vector 4 on the x1, 3 on the x3, and 0 on the x2. So it'd be in the x1, x3 plane. It'd be a vector. And it would be some sort of constant times, because it's just x3. x3 is in R, times that vector. So either one. So you can see it would be the span of V. And you can even rewrite it as some t. You do not need x3/3 there. Or you could use this one, t 4/3, 0, 1. But some t where t is in R, which is all for all t, that is the span. This right here is called parametric vector equation form. So if we look at the original question, describe the set. Here we have it here. It's going to be this vector times any real number, or the span of V, where V is that vector 4, 0, 3, or 4/3, 0, 1, any ratio of that vector. So this is the answer. The solution set is the span of V. That's how we can geometrically describe this. And I wrote the definition with the span of V, any linear combination of V. These are vectors, where t is in the reals, where v is our vector. Now, if we had here one free variable, if we had another free variable, 2 free variables, there'd be another, maybe an x4 here. So there'd be a t and an s. So let's go and see what that one would look like. Let's describe all the solutions to number 8. This is in the exercises in the book of ax equals 0 in parametric vector form, where A is row equivalent to the given matrix. So now this matrix right here is just the A. It is the coefficient matrix since we have AX equals 0. So the right-hand side here, the very last column, is a set of all zeros. And that makes sense because AX equals 0. Here's A times X. X has to be X4. This is a 2 by 4, so this has to be a 4 by 1 to match a 2 by 1. So this row of zeros would be 2 here. And we would get an augmented matrix when we multiplied that out with our column of zeros here. And I'm going to go ahead and row reduce this since we have 2 variables here. Make that easier to find the solution. So I'm going to leave my bottom row alone, and I'm going to get a 0 in that second pivot. So here's my 2 pivots. 0 is already underneath my first pivot, so I'm going to get a 0 above the second pivot by multiplying the second row by 2 and adding it to the first. So we get 1, this would be 0, this would be 4 with a -5, -12 plus 5 is -7, and then a 0 here. So we have that x1 and x2 are our basic variables, and our free variables are x3 and x4. We know that x1 is, if I bring that over, is 5x3 plus 7x4. And x2, if I bring that 2 to the other side of the equation, is negative 2x3 plus 6x4. And that is the solution, but now they want us to describe all solutions in parametric vector form. So let's write it in parametric vector form. So I'm going to write the vector, the solution, the x, in terms of a vector. And again, x was x1, x2, x3, and x4. And we know what x1 is. It's 5x3. We're going to do it all in terms of our free variables only. This one we know is -2x3 plus 6x4. We'll leave x3 alone and x4. And you can see that this is going to be split up into two different vectors. The ones with the x3s plus the terms with the x4s. 7x4, 6x4. There's no x4 in the third one. I put a 0 there, and x4. You add them together, you do get this. So now I can factor out an x3 and an x4. So x is equal to x3 times 5, -2, 1, and 0. Then we have plus x4 times, factor in x4, 7, 6, 0, and 1. There it is. It's spanned by these two vectors. Now these are in fourth dimension, harder to graph, but still that's what that is. So the parametric vector form can be now written as x times some s, some real number times the vector u, plus some real number times the vector t, where s and t are in the reals. And u is our first vector here, and v is our second, which by the definition of spanning, right, this is equal to the span of u comma v. That is the solution set. Or you can say the span of this vector, comma, this vector, and these are vectors. That's it. Now, if u and v were in R2 or R3, we could graph that. If it was in R3, you can see that if it's in R3 and you would have two free variables here, you would get a plane instead of a line. The span would be a plane. We saw that from past videos. So in R3, and particularly R3, if you had no free variables, you would get the span of 0. One free variable, it looked like the span of just one vector. And two free variables would be the span of two vectors, a plane. Since if you had two free variables, you would have another equation here. You would have another x4. So you would end up with a t and an s, a parametric of two constants here, two weights. So it'd be another vector, so it'd be a plane through 0. If you had three free variables in R3, you would have three free variables. So it would be all of R3. Again, we know that is consistent, so it would not be consistent. So you could say it's all of R3. In our next video, we're going to use this idea to find solutions to non-homogeneous systems.